afternoon. I'll be sharing this session until lunch. So first we have Heather Kulik, who'll talk about how to accelerate inorganic discovery using machine learning. So please, Heather.
So many thanks to Roland for the invitation. I apologize in advance. It's about 4 a.m. where I'm coming from, and so if I'm a little bit jet lagged, that's why. So it's my pleasure to be here and tell you a little bit about what my group has been doing in using machine learning for accelerating discovery in inorganic chemistry. And normally I like to cast what we do in the context of being different from challenges for organic chemistry. Unfortunately, I'm going to tell you everything that's hard about inorganic chemistry before the organic chemistry experts step up and give their talks. Pleasantly, I think my talk dovetails very well with our Löwdin lecturer, Marcus Ryer's work, and so I do think he gave a very nice introduction from that perspective. So I will try to go through this quickly to get to some unpublished results at the end. But it goes without saying that in the past decade we've seen dramatic transformations in both hardware and algorithms that have completely changed the face of what can be done with quantum chemistry. And I picked these 2 years because in 2008 I was still a graduate student, and in 2018 I'm a professor with 8 graduate students in my group. So I think about what I could do that does not seem that long ago to me as a student, and what my own students could do, and things that would have been completely inconceivable to me as a student are now things that my own students can routinely do. And so where you can see this is heading is that this is a nice way to think about generating lots of training data. We also have new ways, and Marcus already talked about things like uncertainty quantification, new ways to either improve the methods themselves or understand where they fail. Even things like range-separated hybrids were not quite even mainstream back when I was still a student. There have been really dramatic transformations, so I'd say we've got a couple of more orders of magnitude gain in terms of how fast calculations can go. We've improved accuracy dramatically, but then you can quickly realize that it's not all roses and flowers. This does not mean that my students are somehow writing papers 100 times faster than I could. It does not mean that they are 100 times better at new chemistry, and so there's something else missing. So people are going to keep doing this. This describes the research of many hundreds of theoretical chemists. And what we'd like to do is position ourselves in a place to maximally benefit from this, but think about other problems. And you'll hear about this more today, but you can think about the amount of chemical space that's out there, and there's lots of back-of-the-envelope calculations of this. What we know about this space is that we know almost nothing. And we can think of this space as containing all of the most exciting materials, catalysts, therapeutic drugs that have yet to be explored. And this is not a computational problem, this is a science problem. So this is saying that no matter how hard every person who's currently employed as a material scientist, chemist, engineer, no matter how hard they work, if they keep working the way they work, they will not ever touch even a fraction of this space. And so what we've focused on for the past 5 years is answering the question, what do we need to accelerate this exploration, specifically with a computer and for inorganic chemistry? This is and there are a couple things that we can think about doing. I'm not sure if this is, I think this is just missing from the slide. Yeah. Sorry. So we haven't fixed PowerPoint in that time. So one of the first things I absolutely wanted to do is when I was studying small transition malcomplexes, I would build them by hand. So one of the first things we wanted to do was we wanted to automate. I never wanted my own students to sit there building a molecule by hand. I won't talk about it much in this talk, but think about knowing prediction accuracy and sensitivity. I want to know if I found a molecule that seems like it's the best molecule in the world that's going to solve all the problems. Do I think that just because I used a certain DFT functional? I want to be able to go and overcome the fact that even if calculations are 100 times faster, that's still not fast enough. So machine learning for us is a part of a broader effort to think about how do we get through this space. And then maybe it doesn't really matter how big the space is if we know where we need to go in this space. And how do we start to think about revealing design rules now that we can look at thousands and thousands of molecules at a time, as opposed to, say, a handful of molecules? what kind of design rules can we start to reveal looking at large-scale data sets of molecules? So I will skip through this quickly in the interest of time, but I live in this reductionist world where I'd say that this molecule here is caffeine, and knowing the smile string tells you an awful lot about the molecule. So for instance, you can have a pretty accurate force field that can give you lots of properties. Even before people ever started talking about machine learning as the phrase to use, there were already physicochemical QSPRs. If I wanted to be useful, I could hand the smile string off to someone who had built one of these, and they could probably tell me if it would pass the blood-brain barrier, its solubility, its bioavailability, and so on. And so if we know chemical structure, we know an awful lot in organic chemistry. For that reason, you can think about feeling confident that you can stand on the shoulders of these established techniques. First principle simulation works really well here, and so on. And so I can get a very exact answer for how a small molecule should behave. Similarly, there are these large databases of these organic molecules. And you could think about, well, this is not 10 to the 60th space, but this is an awful lot of space of interesting molecules. And the concepts of molecular similarity are well defined here. So what makes a molecule behave like another molecule? Maybe I don't need to simulate all of these 2 million. I can focus on the 10,000, say, most dissimilar compounds. And there are lots of open source tools for thinking about doing this. So a lot of what you would want to work with already exists in tools such as RDKit and OpenBabel. So this is Rubipi here. Rubipi is not particularly my favorite molecule, unlike caffeine. And to straightforwardly transform structures, even if I could transform the structure into an inorganic complex, I would want to do it in an oxidation state and spin state dependent manner. You've already heard how DFT can be unreliable for these types of systems. When people build QSPRs for them, they're often repurposed. And for that reason, you might worry about standing on the shoulders of a relatively limited number of well-established techniques that can explain the behavior of inorganic complexes. The most widely known databases there have a couple 100,000 or more structures, but they're experimental structures that have been crystallized. These are synthesized compounds, and so they're not that exciting for discovery. If you think about doing discovery, you don't want to do it in a space of things where you know an experimentalist has already published a paper, has already crystallized the structure. That's not that exciting. And concepts of molecular similarity are poorly defined. So I could not tell you off the top of my head why these two transition metal complexes behave more similarly than these two. If you just blindly look at these, you would say there are more atoms with more of the same colors than these two, and so you'd want to group these two together. But it turns out the properties are much more similar of these two. And so we took a divide and conquer approach to this. We wanted to take everything that we thought worked in organic chemistry and find where it failed for inorganic chemistry and just patch it up. And we did this in an open source software we call molSimplify. It does automated generation of inorganic complexes. It outperforms available force fields for getting just what our goal is, which is good starting structures as close to the end of a DFT geometry optimization as possible. It interfaces with those multi-million molecule ligand libraries I told you about, and it creates a syntax for building molecules and interfacing with them on the command line. I will not talk in more detail about this except to say everything we do is compatible, is made possible because of the software. And then we published a paper recently that summarizes this. I think this has a final pub date now. molSimplify automated design is simply molSimplify with a driver for thinking of transition metal complexes in terms of genes, as well as optimizing their properties. And scoring those properties either with a machine learning model or with DFT. And so in a nutshell, what can we do with this? Since this is an ML symposium, as I can say, we do lots of things that aren't ML. And that's to say that we discover how to break catalyst design rules, how to tune properties of inorganic materials for their synthesis, and so on. And so we find lots of uses for this that aren't just machine learning, but when you have a tool now that automates the building and development of training data, it naturally follows that you might want to stop doing all these things. So what I like to think of these as are as chemical space neighborhood explorations. And so this is about 600 catalysts. And what we were able to do was find a new design rule for direct methane to methanol conversion. But those 600 catalysts took a couple months to run with DFT calculations. So then what we did was look at whether there were other ways to do this. When we started out, everything we started out doing in inorganic chemistry, it looks a bit weird to people from the outside because they'd say, well, why aren't you building a force field? Why aren't you building a neural net potential? Why aren't you doing it this way or that way? And what I want to the reason I show what we had done with molSimplify is simply to say that we had something and our goal there was to automate high throughput screening in inorganic chemistry. And so when my student started, he asked me, I'm taking an ML class. What would you like me to predict with a neural net? And I came up with a pretty wacky list of things I'd like him to be able to predict. So I wanted to predict the ground state spin of a simulation. I'd like to know, before I ever do the simulation, can I predict the quantum mechanical ground state spin? And because you've just heard, and because I'm a pragmatist and I know that I don't trust DFT as far as I can throw it, I'd like to know how sensitive that spin state prediction is to the exchange correlation functional that I'm using. And I wanted him to not be able to use any geometric information at all because I wanted to predict the metal ligand bond length. One of the essential things about what molSimplify does is it constructs inorganic complexes, it brings them together, and it guesses the metal ligand bond length that you should need at the end of a DFT geometry optimization. I wanted to know that before doing the calculation. We also predict other properties like redox potential and HOMO, LUMO level, and so on. And we work with relatively small, modest data sets. We've transitioned to a system where actually every calculation that gets carried out in my group now all goes into a central repository, a central database. And even that MAD I was showing, if MAD detects that a calculation it would like to run has already been run, it doesn't get rerun again. We just read it in from the database, so the numbers are much larger now, but they're still significantly smaller than numbers you'll see today. And the reason for that in part is that our complexes, the things we'd like to study, range from about 40 atoms to about 150 atoms in size. We started first with neural nets. And one of the things we did, and I'd like to come back to it at the end, but I always run long, is we used regularization with varying dropout realizations because this both allowed us to avoid overfitting, but also gave us an estimation of the uncertainty of our ML models. And this technique is called Monte Carlo dropout. It's some nice work by Gal and Garamani. We used a very conservative train test partition, and I will come back, hopefully, to these uncertainty measures at the end. And so we started with this very naive approach. We've since progressed to much better approaches, but I'd say the very naive approach works embarrassingly well. So lots of times we're unable to outperform this, but for inorganic chemistry, the way this worked was we came up with various possible feature sets, we assessed them with lasso, then we used them to train more sophisticated models. If they didn't improve lasso errors, we didn't keep those. So it was a very crude feature selection technique, and those features largely came from me as a person who had been studying inorganic chemistry for years. Things I knew had to matter, and I would tell my student, oh, this has to matter. And he would disagree with me. He would say, no, it doesn't actually matter. And so we ended up with things like what is the nature of the metal? What is the nature of the direct coordinating environment? What is its bond order? What are features of electronegativity of those surrounding atoms? We tried to move to more and more non-local features. I insisted the rigidity had to matter, so we ended up with a truncated Kehr shape index. The key thing to note in all of this is that none of this included any geometric information at all. And so we threw away anything that really required global information because it wasn't going to be a transferable model. We ended up with this relatively modest set of features. And the reason why this works, why throwing away whole complex information works, is because inorganic chemistry is incredibly metal local. So this shows a PCA and a whole molecule representation, and this shows two complexes that are 37 or 150 atoms in size. They cluster clustered by size, they are very different, but in property, colored by property here, you can see that they have almost the same exact spin splitting. And so this inherently meta-local representation actually does quite a bit for us. And so the overall result was that it worked. So it was got the correct ground state in 97% of cases. The 3% where it was wrong were cases where the two spin states were so close that if the wind blew one way or the other, the spin state, the ground state definition would change. The RMSE splitting was 3 kilocals per mole, and that certainly is not state of the art. That's not the best answer you'll hear, but for us it was good enough because we didn't trust the training data more than 3 kilocals per mole in the first place. And I used to say this is as good as an undergraduate in inorganic chemistry would know, but I don't really actually know. So I haven't done a survey, but I would bet you finish your undergraduate degree in inorganic chemistry, you probably still can't tell me the ground state of 97% of all inorganic complexes. So it could predict bond lengths. It could also do all of this at arbitrary functional choice, so we could know how we would change our prediction and change our functional and change our prediction. It predicts what I call the DFT spectrochemical series. So I've ordered here these ligands by the experimental spectrochemical series. You can see it's not strictly monotonic. These error bars here are again the from MC dropout. So it could predict metal dependence, it could predict the exchange correlation sensitivity, it could predict bond lengths. So that allowed us to do better than we'd been doing before, which was a database of trained bond lengths. So now the neural net would predict for us what the bond length should be in the complex, and we would build the complex and then do a DFT geometry optimization. But what we wanted to do was not just show, train, and test errors. We wanted to actually do chemical discovery. And that's what I'll talk about for the last bit in my talk today, is how do we actually know, once we've trained a model, that we can use it for discovery. And so I went to my student and I said, we have to do something outside of what we just a partition of train and test. I want you to go into the Cambridge Structural Database and find some molecules we've never studied before. And he said, why do we have to do this? No one is doing this. No one does this when they publish an ML paper. And, you know, luckily he was still early in his PhD, so he eventually relented and we did this. And this is what you find. You can see we only do well. These are color-coded by errors in kilocal per mole. We only do well for a small fraction of the data set. And there's some cases where we fail miserably. If I put on the MC dropout error bars, these error bars don't tell me anything. So the error bars are the same size on the high error cases as in the low error cases. But what we could look at instead was something else, which is how distant in the feature space, which was our MCDL, are the good points versus the bad points. And what you notice is that, although I showed it to you quickly, the points where we were doing well looked a lot like our training data, and the points where we were doing miserably, I had nothing in here. These are cyclams. I had no cyclams in my training data. So so this motivated a heuristic, which was the Euclidean norm of the distance in descriptor space, and a heuristic we set was greater than 1, was too far for our neural net to be predictive. And if you do this, what you end up doing is having the error, because you end up doing a really good job of throwing out the high error points. What I'd like to point out is that means that this hacky MCDL representation we came up with is doing a really good job of mapping it's a really good feature set. So for this type of problem, for spin state ordering, even though it's this very sparse metal-focused feature set, the fact that in feature space, large distances maps well onto cases where the properties can't be predicted does mean that there's some magic that comes about when you have this feature set. And I will show what happens when we lose this. But just to say, what we could then do with this is we could use the distance awareness. So use this idea that we needed to be within a certain distance in order to predict something faithfully with the neural net, and we put that on the fitness function of a genetic algorithm. And so since we were good at predicting spin state ordering, what we decided to do was try to discover spin crossover complexes. And we also could do this with DFT, but it would take us hours for every fitness evaluation instead of a second with the neural net we now had trained. And so this is a small design space we're now doing this with. We did this trivially in one paper I showed you in passing with 20,000. We're doing this now with 10 million molecules at a time, but in this particular case it was only 5,000. So we were lazy, I guess. And so this graphic is a little bit unfair to DFT, just to say in the amount of time that we could find many leads from the neural net, we would be still waiting to get one result out of DFT. And we really did do this. So we tried to use our guess geometries with single point DFT, and that was about 5 days for a GA run versus 20 minutes for the neural net. And the reason it even took us any time, because at the time we were building each molecule and force field optimizing it before we were scoring it. We no longer do that. And so the result is that we have an erosion in error. So we do have about an average error of 4.5 kilocals per mole, but we're able to confirm about 2/3 of the complexes the neural net thought were spin crossover is still spin crossover with DFT. I will show why this was so hard in a moment. One thing to note is that this is a t-SNE of the space that we were working in. And so what we're looking for, this is a hard problem to solve because we're looking for these white crevices. That's where the spin crossover complexes are. And then the black overlay here is where we're not so confident about the neural net because these are high distance compounds. Only 2% of this space had ever been seen before by the neural net. So almost all of it was completely unseen compounds. And so the reason that this was actually hard was because we started all of these compounds between -5 and 5 kilocals per mole based on the neural net, and then we wanted to say that we validated as a spin crossover complex if it stayed within -5 and 5 from DFT. But you can see we started some of these. My student clearly didn't juice the test set in any way. We started some of these at 4.8 kilocals per mole or something, and so we would need the error to be assigned this way in order to stay in this box, right? So we could have made this easier for ourselves, but you can see that very small errors for modest compounds could be observed, as well as the distance heuristic didn't always work if it was chemistry that was inherently missing in our model. We had very large errors for heteroleptic compounds where we had seen the two homoleptics and the heteroleptic combination behaved very differently. And so this would be stuff in an active learning mode that you would actually just go ahead and ingest back into your data set, and that's the way we do things now. But just to say that about 80% of all of our compounds were within 2 times the baseline of our test error. And we made this test hard for ourselves based on where we picked the initial data to be. If we'd started everything out at 0 kilocals per mole, that 2/3 validation I mentioned probably would have gone up to around 100%. So I'd like to move a little quicker because I wanted to show at least something new. But this is just to say we knew that this representation wasn't a very systematic way to do things. Some of our features were more local, and we really had nothing sort of in this mid-range. And so we introduced some new, what I like to describe as a descriptor basis. So this basis on its own is not predictive, but with feature selection, it can identify the essential length scales that matter most, and it's still geometry-free. So we revised and extended autocorrelation functions that have been used in the drug discovery community since the early 80s. And we take 5 properties, the nuclear charge, covalent radius, topology, identity, and electronegativity, and we take the products and differences of these quantities on the molecular graph. There are pieces of it that are essentially what we had come up with in our first neural net, but then there are many more non-local features. This works also for organic chemistry, but just to show some stats really quickly, for inorganic chemistry, this is just to say this is how we did before. These are KRR models because KRR models are more easy for us to transparently test our feature sets. RAC 155 is the full set. These are 2 feature selected sets. URAC means that it was sort of the universally chosen one that's not necessarily the best performer for a single property, but just to say we can learn spin splitting equivalently. Metal ligand bond length, we're now down to below 0.01 angstrom prediction of the metal ligand bond length. We can predict redox and IP. Our most recent paper also predicts homo-lumo gap, homo level, and so on. And what's interesting is you can look at how feature selection here acts on the features themselves. just to say, this is what rack 155 looks like. It's very distally weighted. This is what our MCDL 25 looked like. So proximal weighting is this pink here. And this is what the universal descriptor set looks like. So you can see that we've enhanced somewhat the amount of middle features we have in inorganic chemistry. But the reason MCDL worked so well in the first place is because it's already capturing the most essential things for predicting most of these properties. So this is just to say that when we apply feature selection on the rack feature sets, we can then see that certain properties are more metal local. So we focused a lot on predicting spin. What this map is showing, when the atoms are big, the more they matter more in our features. And so this is showing that spin splitting is in fact very metal local. It's basically telling you that ligand field theory works. Whereas properties like redox and bond length become increasingly non-local and increasingly steric in nature. That doesn't mean that one feature set can't be predictive, but it does give you a roadmap for orthogonal design. You can think about designing features, designing atom properties close to the metal as determining spin state, and atoms further away as tuning redox. But I have literally 1 minute to come back to uncertainty, and I rushed straight through it so I could. This is a rack features neural net. And what we wanted to do was come back to answering the question of how do we address uncertainty. So we had decided that MC dropout was not enough. We had favored, when we had an MCDL feature set, we had favored this heuristic of the distance in feature space. This is a neural net trained with rack 155, and the Euclidean distances in full rack space are no longer useful. The neural net is essentially doing the feature engineering for us in this case, and so we wanted to look at something else. And so this is MC dropout here, and a lot of people are, so you can see that it's not helping us at all. The error bars are all the same sizes. A lot of people are fans of doing instead ensemble models, so training models on different partitions of the data. And so what you can see also is that these error bars are not predictive. They're not telling us where we're failing miserably. And so that was also unsatisfying. So we want to have a general estimation of uncertainty in our model prediction so that we can do discovery. And so what we came up with instead was properties of the latent space. And the result was that we were able to have the error by working in distances in the latent space. And we're also extending this now to organic chemistry data sets. And I completely ran out of time for this, but I wanted to show this very briefly, except to say one of the things we're able to do with, now that we have a feature set that works well for inorganic chemistry, is we're able to actually predict things about DFT calculations besides just the properties that would come out. And one is this case where we've built something that just tells us before we ever set up the calculation, will it give a good result? We judge that two ways. One is by, is the geometry good? Will the optimization just fall apart or fail in some way? The other way is, do we think that the electronic state is faithfully described by a single DFT cone-sham determinant? And in doing so, we're actually able to predict with about 90 to 95% accuracy when a calculation will give a good result. And this moves us towards a new way of using machine learning for automation. And we can also use uncertainty here, uncertainty measures here of the latent space. Here it's the latent space entropy that then tells us when we should trust these classifiers to tell us should I or should I not run a calculation. So just to conclude that we've made some steps in terms of automating simulation and using ML models to make faster property predictions that we normally could with straight density functional theory, and many things still remain, but I'll just finish by acknowledging the students who did the work. Jean-Paul Genet really started a lot of the ML work in my group. And he's a senior student graduating soon, so I strongly encourage you, if you get a note from him, to respond to it. Chen Rujuan, Nick Yang, Adichie Anandi, and Stefan Gugler, who did a 6-month master's with me, also contributed to the work. And thank you.
Thanks a lot, Heather. Do you have any questions? So I was wondering, so this was extremely fascinating, and also the fact that you really need uncertainties is, for me, good to hear. You use PCA and to mainly visualize things, I guess, and you use neural networks. So have you looked at using the autoencoder?
So mostly when we try to visualize what's going on with the neural networks, we usually visualize the latent space properties directly in t-SNEEs. And so, oh my goodness, and so, so that has worked reasonably well for us. But we do wonder about cases where 2 dimensions are not enough.
I was mainly thinking because with PCA you get linear latent spaces, so to speak. With the autoencoder you will get non-linear. So PCA is a special case of the autoencoder. So that
So
might
we
show
only
you
most of what I
different things.
showed, including the latent space visualizations, were t-SNEEs, not PCA.
Okay, fair enough.
Yeah.
Any other questions?
Mm-hmm. So that's what molSimplify already does. I showed the first generation very, very quickly. molSimplify sets the input, and the thing I showed at the end there is precisely something that says, has the calculation succeeded? I showed the static classifier. We also have a dynamic classifier that now reads electronic structure properties as the calculation is running and decides if it's not working. And that's a convolutional neural net. And it uses descriptors. What I showed with the static classifier is a no-cost determinant of is this a good calculation, yes or no. And that's essential in inorganic chemistry where the calculations can fail many different ways. Sorry, you were asking about automation. Yeah, so the molSimplify, the first thing it ever did was generate input files only with sane combinations of input files, and generates a good initial structure. That was the first thing it ever did. The next generation, what we've published since then, is things that also decide after a calculation has run or after the structure is generated, do we think that the structure is still a good structure, both in terms of its electronic and geometric properties. And then the newest iteration are, do I think before I've even set this calculation up, will it lead to a successful result? And that's what we're able to predict with 95% accuracy, even on diverse training and test data. Yeah.
Let's save that question for afterwards. But so let's thank Heather again. Thanks a lot. All right, so the next speaker is Anatole von Lilienfeld from the University of Basel in Switzerland, and you've all seen what he will talk about, so welcome, Anatole.
Really a pleasure to be here. Thank you so much for having me. Greatly enjoying my time, and these are really wonderful talks. So I'm pleased to tell you all about some activities going on in my lab, and we are also interested in chemical space. And I'd like to start out with a mentioning of a machine learning special issue in the Journal of Chemical Physics, which was co-edited also by Matthias Rupp and Kieran Burke, and there are many great contributions from the community on this burgeoning upcoming field. I have a little table of contents here. I'd like to briefly motivate why we do what we do, and then I'd like to tell you about 4 papers, and which are recent. The first one is already published in this issue, but the other papers are still under review. I hope to get through these. Now, the people who did the work are Bing Wang and Felix Faber and Anders Christensen. Matthias Rupp also used to be here, so but he will tell you about his own work himself. So as you know, chemical space is huge, and in the biological sciences in particular, people have been thinking about this for a long time, and there was a Nature Insight in 2004, where actually a number was given, something like 10 to the 60, for the total number possible in terms of medium-sized organic molecules. So it's still a very small subsection. And actually, atoms in the solar system is something like 10 to the 54. So we don't have enough atoms in the solar system to make the hard drive to store the list of possible molecules. Right? So that's the problem. I think we continuously underestimate the size of the space. And there's a quote from Al Butler who also points that out, that that's a human thing. And so when we want to explore the space, what we often encounter is that people think about molecules differently. And I like to think of it this way. And in my lab, we try to assume the first principles attitude. We are part of the Physical Chemistry Institute, and we like this idea of using quantum mechanics to study chemistry. And within quantum mechanics, it's actually quite well defined what a molecule is. So the first postulate of quantum mechanics really tells you your system is a wave function, and the Hamiltonian, of course, then offers gives you the procedure of how to get to this wave function. And if you look at the Hamiltonian, there's the external potential, and in the external potential you have the nuclear charges and the atomic coordinates. So it's all very well defined, and there's no question about what actually constitutes your system. It's not up for discussion, if you wish. And so in the space of nuclear charges, coordinates, and number of electrons in some unperturbed system, you could every compound could be a point, and this could be N2. And you can go from one compound to another, and actually your electronic Hamiltonian is continuous even in chemical composition. So your nuclear charge can be a real number, and you can continuously go from one to another. And in another line of research in my group, we explore this with perturbation theory. And here you see such perturbation-based results. You have the electronic density of N2 in this corner here with CCSD level of theory. And you can perturb it with respect to such a walk in chemical space. And so here you see first, second, third, fourth ordered perturbations. And now you can use these perturbations to estimate the electron density of CO, of BF, and this works quite well. So from quantum mechanics point of view, this chemical space is actually a good thing, or well defined, I think. And so if you choose not to use quantum mechanics, right, then of course you can make such a choice. But here I like this quote: we can ignore the quantum reality, but then you cannot ignore the consequences of ignoring it. Or more humorously, never turn your back on quantum reality. It surrounds you. So in quantum mechanics, you all know that we have these hierarchies of methods, such as force fields, semi-empiricism, Hartree-Fock, MP2, quantum Monte Carlo, or coupled cluster, or the DMRG. And this is also true for basis sets. And we like to think that our errors compared to experiment decay as you invest more CPU time. And what I think is the real power of machine learning is that we have something similar. As you increase your training set size, the error of your machine learning method comes down. And this is why I like to call it quantum machine learning. So it's this combination. It's we inherit many nice properties of quantum mechanics by systematically being able to lower our errors here. And Vladimir Vapnik in the 90s and others actually showed that your prediction error decays inversely with training set size. And because of this, they already then recommended that we all plot prediction errors as a function of training set size on a log-log scale. And like this, we can easily compare the performance of different methods, and we can situate ourselves well in this universe. So we really use these learning curves a lot, and so a lot of our machine learning research is about how can we lower these curves or improve the slope And recently I published a little perspective on this, if you want to hear more about my attitude towards this. So this was the introduction, and now I'd like to tell you about our work on representations. And this really started in 2011 when I organized a long program at the Institute of Pure and Applied Mathematics at UCLA. And Klaus Robert Müller came together with his postdoc Matthias Rupp, and they are machine learning people. And so we started to discuss these things. And the question then, they basically told us, well, it's all well defined, so it's a really simple problem. You can use kernel-ridge regression, which is sort of the poor man's machine learning method. And we can just learn this. The only thing we need from you is a representation. So how do we measure similarity? In other words, some sort of quantitative procedure to establish a chemical space. So every compound here is such a point, and then how do you define these points, right? That's really the question. And so what I then proposed to Matthias actually was, let's use this Coulomb matrix, which is a distance-based matrix. On the off-diagonal elements, you have the inverse distance, and as a nominator, you have the nuclear charge product. And on the diagonal, you put the nuclear charge to the power of 2.4, which is a rough estimate of the energy of the free atom. And so this really corresponds then to the complete graph of any given configuration. It's the simplex in your geometry, and that is a unique representation. It's complete. You don't lose any information, and for that reason, there's no noise, and you expect your learning curve to systematically come down to arbitrary accuracy as long as you increase your training set size. And so Matthias programmed this, and we could see that for organic molecules, indeed, your atomization error would come down in the manner we expected. And we reached 10 kcal per mole at 5,000 molecules. And so this is on par with GGA, DFT. And so this really encouraged us, and we wanted to continue this. And since then, a lot has happened, and we now have a new data set. It's called the QM9, which was published in 2014. It contains 134,000 organic molecules with various properties. And on that data set, this Coulomb matrix has this learning curve for the atomization energy. More recent adaptation of the Coulomb matrix called the bag of bonds. It's just bagging entries or elements from the Coulomb matrix, gives you this learning curve. So something improved. Now we were wondering, what is it? How can we really improve this in a rational way? And here's a little experiment. If you want to learn a Gaussian function, shown here in red in the inset, using as a representation a linear function or some other function, right? You can ask this question, what happens to my learning curve? Actually, if you use a quadratic function, also shown in the inset here, you don't have learning. And the reason for that is that this function is not unique. Clearly, as you provide this as an input, your machine will not know if you're referring to this segment of the curve or to that segment, right? So there's a noise level. No matter how big your machine, no matter how large your neural network, you will never be able to improve this. And so this issue of uniqueness is really important. And in molecules, you can actually see this. This is an example of two molecules. If you arrange them in certain geometries, for instance, in planar NH3 or in a tetrahedral NH3 arrangement, you can have the distances such that all the interatomic distances are the same in both sets. And so then you cannot distinguish them anymore if you have a pairwise representation. And this is shown in this figure here. If you use, for instance, the Lennard-Jones potential, so just a pairwise interaction, the energy for these two clusters as a function of a scaling factor is the same. It's the dashed figure, the dotted figure, I'm sorry. It's only after you introduce free body terms, the Axolotl-Muto terms, that you can distinguish these two and that the spurious degeneracy gets lifted. Now, this is really crucial because this means if you have a non-unique representation, your machine will not converge with training set size. Now, put in something unique, for instance, this linear function, sure enough, you get learning. Put in an exponential, just exponentially decaying, showed here in dotted, you get the same as linear. Now, in the exponential, you can increase the exponent, of course. So here's the exponent shown, and you increase it by a quarter, your learning curve comes down. You increase it more, your learning curve comes down again. You increase it to 2, you get the red. So now this is a Gaussian as your representation, trying to learn a Gaussian function, right? And it turns out that the learning curve is the lowest. If you increase it even further, it comes up again, right? So you have a manifold of possible machines, and the best one happens to be the one that uses as a representation the very function you are aiming for. So this led us to believe that what you really need to have is something that models the truth, right? And so we should include the right physics, the true physics, in order to be able to learn the right physics. And we tested this using, again, the Coulomb matrix. And the Coulomb matrix is just 1 over r, and that's what you see here in blue, right? Now, if you play with this exponent, put it to -1, then you just have a linear function. And sure enough, you can learn this. It's still unique. But the offset is worse, right? So you're worsening your physics, and your machine has a harder job to learn this. To make it even worse, we put it to quadratic. So we use this as a representation, the black curve, and things get even worse, right? Conversely, if you increase the exponent, you see that your learning curve improves as well, and so it's optimal around 468, so common London dispersion power laws, and then for 10 it comes up again, right? So again, we could see that something more physical improves the machine. And so then it was, of course, plausible to say, well, let's put in a force field, right? That should be a good model of what's happening. And so we used the universal force field from Goddard. We put in bonds and angles. Therefore, we call it BAML, so bonds, angles, machine learning. But there's also a torsional term, so you can go up to 4 bodies. And sure enough, for these molecules here, you see the bonding representation. Now you add the angles, you get the red, and you add the torsion, you still get an improvement. So systematic improvement as you include more of the right physics. So this is what BAML looks like, and this we published in 2016. In 2017, we published a paper in a collaboration with Google, where we got an even better representation, which was based on a distance distribution, simply the distributions of interatomic distances, simply a histogram, and it outperformed the entire force field discussion I just showed you. So we thought, okay, let's combine the distance distributions with something more physically motivated, and this has led to the London Axorotella Muto, the LATEM representation, and you can turn this into a distribution or a spectrum by just doing the histogram on this, and this is how it looks like for the distances and the angles. And you can do this for every atom. And if you then look at the learning curves, here you have the Coulomb matrix, Bob, LATEM, the distribution is LATEM, and the atomic LATEM, you see now still a systematic improvement every time you do this. And to push this even further, because LATEM really is tied to this functional model of dispersion interactions, we wanted to have something more systematic, so we decided to develop a representation which goes up to m bodies, and every body here, so distances, angles, torsion, etc., is represented by Gaussians, and the one body term is the period and the group in the periodic table. And then the two-body term is a Gaussian distance-based distribution, which we scale by this function chi, which contains these power laws, like you would have them in a Coulomb power law or London dispersion power law. And you can do this up to arbitrary bodies, and when you calculate the distances, all you get are actually distances in Gaussians. So here this is done for the two-body and the three-body term. And again, in both cases, you see these chi functions which scale things also for three-body, and they are very important because they improve the performance a lot. This is what we call the FCHL representation, and if we come back to these learning curves, this is the black line. So it's currently the best representation we know of. There are many others. Here you also see the Slatem representations in here. The A Slatem is the purple one. The SOAP representation was published by Zani, and Michele Ceiotti is the yellow one. And meanwhile, there has also been a convolutional neural net from the Google collaborators, and TensorFlow machine in blue. The most why does this representation work so well, the FCHL? If you do a PCA on the kernel, you see that this is an extremely encouraging result just for the first two principal components. By comparison, a kernel PCA on the Bob representation looks like this, right? And on the Coulomb matrix, it looks like this. So we believe this FCHL does something really good in capturing and mapping out the chemical space on a lower dimensional manifold. The most recent results are now shown here, and you see all sorts of institutions have been contributing, and we are all approaching this sort of minimum model you see here. And so this triggered our interest in actually launching a competition or a challenge. We call it the QM9 IPAM challenge. We are looking for a model which reaches chemical accuracy with just 100 training instances. Now the panel is a bunch of professors, and everybody committed to donate $100. If any professors are in the audience who wish to join this panel, please let me know. Obviously, the incentive is the more professors there are, the sooner we will have somebody who will put forth such a model. With this, I'm done with the representations, and I'd like to go to this multiple level approach. Markus Reier mentioned before that he had an error estimator of his DFT predictions, and this goes in the same direction. If you think of Popel plots and the model chemistry, you know that in terms of basis set size and in terms of correlation treatment, we believe that you can approach this exact solution. And the question is, how can we get there, combining all the different levels of theory? And we wanted to explore this with machine learning. And so using different training sets on different levels, we also hope to approach the exact solution more rapidly by requiring less of the most expensive instances in order to make predictions which are still as accurate as the most expensive calculations. And we did this in collaborations with a mathematician at the University of Basel, Helmut Habrecht, who is an expert in what's called the multi-level combination techniques. So we call it CQML. And it basically is a recursive formula where you train machine learning models on every level combination you can imagine, and you can stitch them together. And what you then obtain are learning curves such as these. And in particular, look at the 3D models. So the 3D models exploit electron correlation treatment, basis set size, and chemical space. So that's why we call it 3D. And we have two flavors because of how you what's the ratio between the number of molecules at different levels of theory. And so the ratio for S equals 2 is the most advantageous, and you can see here at the most expensive training molecules you need to get chemical accuracy. We estimate that you need 100 of those. Why didn't we converge this curve further? The reason is simple. We would have required over 25,000 Hartree-Fock calculations at the lower level to be able to go there, but this training set, the QM7B, only has 7,000 molecules, so we ran out of molecules. But in principle, we could do this for larger training sets. The third paper I'd like to tell you about is on scalability. We developed this idea that when you have a large query molecule, you could think of it as a bunch of atoms with a chemical environment. So suppose they are atoms in a molecule, and this is not Beta's approach, so we don't want to call it AIM, but so we just dub it M, and then on for some sort of quasi-particle. So the amon is then a fragment where you have individual atoms surrounded by their environment, and so in some sense it's an extension of the periodic table where you include the environment as well. And so if we look then at the machine learning model, right, this was the usual model. You just with the kernel-rich regression, you just sum over your training instances and you weight that distance. We can write that distance as a double sum of atoms in your query and atoms in your training molecules. So if your training molecules are these amons, then the number of atoms in the amons can be much smaller than the number of atoms in your query molecule, and that allows you to scale, right? So that's the basic trick. And so imagine you wanted to account for this OH group. You can then use as a training molecule water. You can use methanol, propanol, ethanol, and propanol, right? And as you increase the amon in size, you would expect that your predictive accuracy improves. And this is exactly what we see. Here you see for various properties, machine learning predictions, and you see the deviation from the target property, from the target molecule, as a function of number of amons and size of amons. So the little number here shows you number of atoms in the amons. We go up to 7 atoms in the amon. This molecule has 9 atoms in total. And you can do this for all sorts of properties, right? And you see quite rapid convergence. Now, this is scalable, so it also works for Shignolin, the hairpin peptide model. And here you see also with 7 atoms, you get to chemical accuracy for such a large system. And finally, we even did it for ubiquitin. There's a protein. And I just checked our numbers again. So the reference here is a hybrid composite method recently put forth by Grimm et al. If you want NMR shifts, you have to use Orca, which is quite slow for this. I think it's not optimized, but it took us 4 CPU years to get the NMR shifts on this thing. To get the energy is 3 CPU hours using turbo mode. But still, so just with 7 atoms in your fragments, you can get to target accuracy. So we like to think of this as the DNA of chemistry. And why is that? If you think about letters, they form words, which are the building blocks for a sentence, and out of that you get meaning, right? Now, atoms, they build up DNA, and DNA defines a gene which has some function. And in our case, the atoms, they go into amons. And these amons then form your query molecule, and you can predict a property from that, right? So for us, we think of amons as the DNA of chemistry. And here, this is illustrated for 3 molecules. These are the amons, and you see some of them overlap. So these are amons you can use for all these 3 molecules. So once you have them, it's like a dictionary. You just look it up, you make your prediction, right? With this, I'd like to go to the last chapter. We looked at response properties. Within kernel-rich regression, your energy is just this matrix product of kernel with the alpha, the regression coefficient vector. So if you have some differential operator here, which works on your energy, this propagates through to your kernel. And you can write then your loss function in the usual way. You write it out, and then you solve for your alphas, and you get this product of these 2 matrices. And we can identify these matrices The first one contains a product of the derivative of your kernel matrix with respect to your differential variable. This is this eta. The transpose times itself again. And here you also have the transpose times the derivative of your reference property. And this is something you would like to use then to train a model on response properties. We see that for forces, this improves things. If you have a binding potential like this, you see that with and without forces, your machine learning model improves a lot. And we did this for a couple of data sets, and you see nice learning curves with improved models. Also here you see much improved models for forces. So with these you can get geometries and relaxations. And here you see a combination of Amons predicting this large molecules, and using the force machine, you see that as a function of training set size, your normal modes become increasingly better, right? So you converge in all your configuration and degrees of freedom, your accuracy. Now, forces are not the only differential operator. There's also something called an electric field with which you can derive, and then you get a dipole moment. Of course, you saw that the derivative in your loss function contains, you have to derive your kernel with respect to the variable. If your electric field is not in your kernel, this derivative is going to be 0. So it's not going to be meaningful. So you need a model, you need a representation that accounts for all variables, including the electric field. And so we updated our representation, the FCHL, to contain also classical dipole moment. And using this, you can get the dipole moment of a molecule in a field. Here's the field rotating, and you see with the representation we can capture it. And also the learning curves in QM9 dipole moments improve a lot. Of course, you can put these things together and actually learn an AR spectrum of a molecule by increasing training set size on dipole moments and normal modes. You converge towards the MP2 prediction. These developments are in the QML code, which is on the GitHub, available for everyone. And with this, I'm at the end. I thank you for your attention.
So while we're switching computers, we can take 1 or 2 quick questions, perhaps.
Do you need this?
All right, let's thank the speaker again. Thank you. All right, the last speaker before lunch is Maria Chan from Argonne National Laboratories.
Thank
Please.
you. Thank you very much, Roland and Morgan, for organizing this session. Thank you for the invitation. I am not a quantum chemist. I'm not a chemist of any type. So you'll hear about something slightly different. I'll also talk about experiments. As far as I know, I'll be the only one talking about experiments. So I'm going to be doubly weird. So what I'm going to talk about, first of all, let me give you an introduction. I'm from Argonne National Lab, which is in Chicago. It's one of 17 U.S. Department of Energy national laboratories, and it was developed for nuclear energy. It was built for development of nuclear energy, but we have branched out. The work I'm going to talk about is done by several of the very enthusiastic and talented postdocs and students. And then in our group, we do a lot of different types of modeling. So the bread and butter, I would say, of what we do is understanding renewable energy materials, primarily batteries, solar cells, and catalysts. And then another aspect, which I won't talk much or any at all today, it's about more accurate prediction of properties. Things like phonons, how to deal with anharmonic phonons on unstable crystal structures. Also, more accurate absorption energies using quantum Monte Carlo. But then the third part, which is becoming more and more important part of what we do, is how to tie in all the modeling that we do with experiments. A lot of that came out of necessity. I'm surrounded by experimentalists working in a national laboratory in very collaborative projects. And oftentimes I would have very exciting results to tell my colleagues, and they said, how do I know if it's real? How can I see it? And so on and so forth. So it becomes more and more important for us to actually try to connect more closely what we do with what the experimentalists actually measure. And increasingly we use machine learning for that. So what I'm going to talk about today is one specific example of that problem, which is how do we know what are the structures under measurement in the experimental system, the arrangement of atoms. So in the experiments, characterization experiments in particular, there is usually a beam that's shown on the material, electron beam or X-ray beam, and you get a signal out of it. About 70% of the time, it takes weeks, months, or maybe even years for the experimentalists to figure out what that signal actually means precisely. So the problem that we have is actually how to do this inversion, how to go backwards, taking the signal that they measure directly and using atomistic modeling and first principles modeling to get the atomistic structure that are under the sample. And we do this for a wide variety of different characterization experiments. So this is the alphabet soup. You get used to it if you talk to a lot of experimentalists. There are different types of measurements that are undertaken. All the ones that start with X that have to do X-ray. X-ray diffraction you're well familiar with. There's X-ray reflectivity, which is a kind of single crystal diffraction that allows you to very accurately tell positions of crystals at interfaces. There's things like pair distribution function, which I'll talk a little bit about. X-ray absorption and other core level spectroscopy, such as electron energy loss, non-elastic X-ray scattering. There are more optical types measurement, such as Raman and UV. I won't talk about this. And then a lot of our work comes from electron microscopy, transmission electron microscopy, TEM. All right. So what is our strategy? How do we facilitate this inversion of characterization data that is being measured? So what we've built is a framework that we call Fantastics. It's fully automated nanoscale deterministic structure from theory and experiment. I have to practice a lot of times to say this without breathing in the middle. We like the acronym, it's fantastic, but actually the spelling out of the words is a little difficult. So the general idea is the fact that you can use a combination of experimental measurements and energetic information. So the problem here is that we can do a lot of calculations and get a lot of plausible properties and structures. The problem is that we are in the computational, we're a little bit under constrained because we can do a lot of calculations even for very non-physical type systems. In the experiments, they are kind of underdetermined because they actually don't have enough information most of the time to figure out what their structures are. So the idea is to combine both of those using energetics to help the experimentalists determine if the models being considered are physical, and then also using experiments to constrain the calculations a little more into more physical space. So using this sort of two-loop approach and appropriate sampling strategy, such as a lot of the ones that were mentioned before, Monte Carlo with classic examples like genetic algorithms and so on. We hope to try to find out what the structure is that is consistent with experimental measurement and also computationally plausible. So these are the different parts of the ingredients that are needed to achieve this Fantastics framework. Of course, the first thing is we need to be able to sample a lot of different atomic structures, and that's no problem for many of us in the chemical materials and physics modeling community because we've been doing that for many decades. So I'll just go through it briefly. We need to be able to efficiently predict energies or large computers, either one of those. And we've heard excellent talks earlier about how to improve this efficient calculations. Apparently my head is too big for this. I'm sorry. All right. falling off. All right. Oh, much better. Okay, it's not that my head is too big. I'm unable to rotate it properly. So thanks for the adjustment. Okay, then the third and perhaps the most important part is how do we go from the atomistic structure we have to characterization data that they would measure accurately and efficiently. That is actually a part where we spent a lot of our time on because it turns out we're not always very good at it. And then finally, the appropriate optimization algorithm. So we'll start with the first. Sampling, as I said, is something that we've been doing for decades. So there have been in the materials community. Oh, so that's the other way that my talk may be a little weird compared to the rest of this symposium is the fact that I'll talk a lot about solids. So in the solids community, there have been also structural databases that are more or less exhaustive in terms of crystalline structures. There's also previous approaches for sampling positions if you are on lattice, like cluster expansion. Genetic algorithms, which I'll talk a little bit, and then other history-dependent sampling for non-equilibrium type structures. So what we do for a lot of nanostructures is genetic algorithm, and many of you would be familiar with it, but in case some students are not, the general idea is that is borrowed from biology. Suppose you have a large number of different nanoclusters, which in this case is very similar to a molecule. You can create random structures out of those and then pick any two to be parents and then combine them in a physical space. So essentially cut and paste the nanostructure of molecule and then create more mutation by changing the atom positions, atom species, and so on. And then finally evaluate the fitness, and you can use density functional theory, which is primarily what we do. But remember, fitness here isn't just energy anymore, because we're interested also in how well it matches with experiments. So that we include the different types of fitness in there, and that's the key difference. So for energy-only genetic algorithm, I give you an example for gold nanoclusters. So gold is interesting for those of you who work in catalysis. Gold is a catalyst for CO oxidation, for example. But gold is also interesting fundamentally because 13 atom gold clusters are believed to be planar, unlike all other known metal clusters which form 3D structures as soon as there are 6 or 8 atoms. So we're trying to figure out if we can use GA to genetic algorithm or GA to efficiently determine the low energy structures. And we can do that by not constraining the positions of the atoms or by constraining it to 2 dimensions. And we find that in both cases, we end up with low energy 2-dimensional structures. They're a little bit different, but if you constrain 2-dimension, you get it much faster. So none of that is a huge surprise, but just to build part of the machinery to be able to do the sampling that we need. All right, efficient prediction of energies or large computers. Some of the previous speakers mentioned that they didn't want to build force field, but we didn't mind building force field. So we also use genetic algorithm to build force fields that allow us to sample faster, essentially. So in the previous example of gold nanoclusters, we determined a force field that seemed to be effective. It's a hybrid bond order potential, which has a short-range term with a Chersoff-like term and a long-range term that's Lennard-Jones-like. So with the potential, we have about 17 parameters, and we determine those parameters again using genetic algorithm. In this case, we turn the parameters into bit strings and combine the bit strings from 2 different parents and also form mutation. So these parameter sets give you these results. This delta here is the total error in the energy compared to DFT over 1,200 gold clusters. So we calculate 1,200 gold clusters using DFT from the previous genetic algorithm optimization of the structure. So you see that over a small number of generations, the errors come down. And then this is the plot of the force field energy versus the DFT energy. This is the new potential. These are existing potentials for gold. There are a lot of potentials for gold. So whoever wants to work on gold, please be very careful. There's a huge community of people who work on gold who are very protective of what they found about gold. But it's interesting. A lot of the force field actually do really well in terms of a correlation with DFT energy, even though there's quantitative error involved. But anyway, so we've also in order to carry out more of these, and also for other reasons, we fit a number of force field for things like iridium oxide, nanoclusters, and also nanoparticles. Two-dimensional materials, such as two-dimensional tin, stand-in. And in this case, we didn't just fit to the energy, we also fit to the phonon dispersion, because we wanted to be able to calculate thermal conductivity with this force field. So now we've had about a dozen systems where we have successfully used the genetic algorithm to fit force fields, and then we've convinced ourselves that we are able to do that for further systems of reasonable complexity. So now we think we can efficiently calculate energies. We also have larger and larger computers, and then we're able to scale the code to run in parallel. So that then comes the key part, like I said earlier. How do you calculate characterization data, not just accurately, but also efficiently? So then we run into, again, a different community of people who have been doing characterization data calculations, and those are the experimentalists. One thing I found about experimentalists is that they really like their GUIs. So this is, for example, is a X-ray diffraction refinement code that's used by thousands of users. And it's entirely GUI based. So you enter the structure, fill in the little boxes, and then you enter different parameters to fit, and then you click the button and you wait, about 30 seconds, and it'll give you the results. And if you think about this type of framework, it's very difficult to do any kind of automation. So one of the things that we had to do first is to write a scriptable version of this code. And this is sort of similar to some of the other stories where the technique to calculate the data is well known, it's there. But the code being used is not very scalable, and we had to make that more scalable. In another vein, if we want to calculate X-ray core level spectroscopy or electron core level spectroscopy that measures the excitation of core level electrons, we had to use higher order calculations, such as the beta-salpeter equation, because DFT, of course, is not accurate, but some of the more simple approaches like multiple scattering. So this is the X-ray absorption near its spectrum for copper KH. Black is the experiment, and then green is a previously widely used calculation code called FEF. And then we find that no matter how you tweak the parameters, the accuracy was not there. But using beta-salpeter equation-based approach with a new code called Ocean that Eric Shirley and John Vincent developed, and we again work to parallelize and make the workflow better. The accuracy is much better. And similarly, for a number of 3D transition metal core level spectra, black is experiment, red is the calculation. Even for non-KH, the accuracy is really pretty good. And I'll skip over this one. And then sometimes the simulation of the characterization data isn't just one-dimensional plots, it's two-dimensional images, such as scanning tunneling microscopy or electron microscopy. Again, they are existing codes. A lot of times we have to improve it, make it scalable, make it more accurate. And then that was all about calculating. But then we're not done, because we can calculate some characterization data, but the comparison with experiments is not always straightforward, especially when it comes to two-dimensional or higher dimensional data, such as the image, electron microscopy image. So we had this previous problem, they say the mother of invention is, necessity is the mother of all invention, right? So we had a previous problem where we had to figure out what the deterministic structure is for a grain boundary from an electron microscopy image. And we did that by very crudely, putting in the structure and then tweaking the atoms by hand, trying to sort out, if these are too close in the two dimension, and then improving it and so on. And in the end, we get something like this. So the under black and white is the experimental measurement, the electron microscopy image. The red and blue are the structure overlay on top. And embarrassingly, what did we do? We open up a PowerPoint slide, and then we make the scale the same, and then we eyeball and see, are these close, right? This was where we were several years ago, and this was not good. So we needed to develop some approach to compare a simulated image with an experimental image with the understanding that they have different noise levels. They don't always have the same orientation, and so on and so forth. Fortunately, the most straightforward or the brute force way to compare two images is if you take them as matrices, align them as well as you can, and subtract them and get a mean square error. So that's what we call MSE. There also were some previously developed approaches in the computer vision community that measure similarity between two images, mostly to test the lossiness of compression algorithms. This is called SSIM, Structural Similarity Index. But then we also noticed that our problem is very similar for computer vision problem like facial recognition. So the way that facial recognition works is a lot of times by turning a face into a set of points that describes your features, the corner of your eyes, the middle of your eyebrow, and so on and so forth. And the faces are compared feature to feature via those points. But then we already have features like that by the atomic columns in electron microscopy. So we essentially adopt this method by clustering the points, comparing the nearest neighbor distances and orientation, and then turning each image into a set of vector with these features, and then comparing the vectors using clustering. So with that, hopefully this works. Yeah, this is an illustration of how that works. So this works irrespective of the orientation as well as the noise level of the images, and we can tell which part of the images are corresponding to which other parts. A bonus that came out of this that it turns out to be super useful, even though it's not necessary for what we want to do, is what's called image segmentation, which is dividing up an image into qualitatively different parts. So for example, here is a crystal with a defect in the middle, the dislocation core. And the automatic segmentation allows you to tell, okay, the blue atoms are different from the red atoms, and then there's the green atoms that are even different because they have different local environments. So this is an experimental image, same thing, we can get segmentation. This is sort of a more challenging one, it's more noisy, it's lower resolution. But nonetheless, after some filtering and the feature-based selection clustering, we're able to separate out the two crystals at the interface. But back to what we were interested in, comparing two images to figure out, one simulated, one experiment, to figure out how close they are in an automated fashion, without any human intervention. So to do that, we created simulated image data sets and several thousands of images. But then we added different levels of noise and so on, so that becomes about 60,000. And then compare the different approaches to match those images. The blue is what we had, like the one that's similar to facial recognition, the cluster-based approach. The red is the brute force alignment, subtract two matrices. You can see that the blue is always better than the red, or even similar when you add a lot of structural defects. But in terms of having different amounts of blurriness, the cluster-based approach is definitely much better. We also find that the structural similarity index, which is what the computer vision people developed to look at how much an image degrade after compression, also does reasonably well and better than the cluster-based approach if you have a highly degraded image. So now using that, and I can skip this, using all of these tools that I've talked about, different ways of sampling, calculating characterization data, evaluating energy if needed, and also comparing the calculated and experimental signal. We have a couple examples to show, putting all together. So one of the simplest examples that we tried is on X-ray pair distribution function, which is plotted here. It shows you, given a central atom at 0, what's the likelihood of finding another atom at a different distance, at various distance. So the first peak is sort of the first nearest neighbor peak shown. So we use these gold clusters. This is now a 14-atom gold cluster that's like a pouch-like shape. We simulate a PDF. So this is synthetic artificial characterization data. And then we ask the question, can we find it back? All right, so the first thing we do, of course, the experimentalists have not been sitting there waiting for modelers to try to come up with a solution. They have their own approaches to find a structure. Some approach basically has to do with essentially like a reverse Monte Carlo-like approach, moving the atoms around and checking the fit to the PDF until it's low, the errors are low. So this is an example of using those tools to find a structure that gives a good pair-distribution function. And you can see that this structure looks nothing like the target, right? Nothing like what we started with, which in itself may not be a problem. Maybe it is also a good structure, just has happened to have the same PDF. However, when we check in DFT or the force field, the energy of this structure is extremely high. So that means it's probably not physical, even though it matches the PDF. And this goes back to the problem of underdetermination from the experimental data. There's not enough information in the PDF alone to tell what structure. And then similarly for DFT, and we actually use PBE for these gold clusters because it was surprisingly shown to correspond the best to couple cluster data for 8-atom gold clusters. So this is PBE without spin-orbit coupling. We find that a lot of structures actually have very similar energy. If we look at energy alone, in fact, these two structures that look very different have exactly the same energy to 3 decimal places in PBE. So we have the same problem. We can't tell which of these structures should exist, even with reasonably accurate methods. All right, so what we do is take these two examples, these two gold clusters, lowest energy and also higher energy cluster, and then we put it into a multi-objective optimization algorithm using genetic algorithm. So what that means is that we don't combine the two objectives. We allow the exploration of both objective space. And then we find the non-dominated solutions at essentially the Pareto front. But when you have a target structure that is optimal in both, then very easily we find that point. It's the lowest in energy, also best fit to the PDF. But however, when you have a structure that's not, that is the PDF is of this structure, but it's much higher in energy, these are in EV scale, much higher in energy, we're still able to find it, and also several others along the Pareto front. So that was an example with synthetic data. What about real data? What about real experimental data? So this is an example, again, I showed you earlier, of an interface taken with STEM with their noise and everything, putting into the Fantastics framework with the image comparison tool that I've talked about. What's shown here is animation of the process of taking 2 pieces of crystal, and what we're really interested in is the structure at the interface, which is the one that's most ambiguous. The lower right is the experimental data, and you can see it's not sort of clear-cut dislocation cores like you would expect of typical grain boundaries. And then this is sort of the simulation. At first, it goes faster because more atoms are being sampled, but then later on, the region that's being sampled is lowered. What's shown here is the combined objective of both the energy and match to the image. And it goes mostly down, but we also take steps from that might increase it just to sample more space. So in the end, you get a structure that is very similar. We also get a lot of different structures that allow us to explore for different degrees of similarity to the experimental image. What are the difference in energies and, more importantly, electronic properties and so on. So just for fun, we turn off the requirement to match the experimental image and just let it go. And of course, as you might expect, the top grain the top crystal just starts growing because the lowest energy structure has no boundary. Of course, this is one crystal. And that also brings us to the point when we do sampling using energy only, oftentimes, unless you have some very clever way of constraining it, you're really only sampling the very low equilibrium type situations. And that's not at all relevant for a lot of type of realistic situations, such as in electrochemistry or when you have extended defects and so on and so forth. So, okay, we can do that. We get the structures. Then what? right? We don't want to be, as an earlier speaker mentioned, we don't want to just tell the experimentalists what they already know. They said, this picture looks just like the picture I took, so what? So one of the things that we can do with a 3D atomistic model is to be able to do material design, like previous speakers have talked about. So in the case of the defects in this grain boundary, or this extended defect we talk about, we can put in different types of atoms to try to passivate the dangling bonds, and this is for photovoltaic applications. And that's not all. Another reason that we want to do this is to allow, and in previous we could talk about real-time calculations. What we want is real-time inversion because experiments are being done, and a lot of times these experiments you require billion-dollar equipment, and the experimentalists have like 3 days or 7 days to do it. If the data is not analyzed until 2 months later, they can't adjust their strategy. So what we want to do is to be able to tell, in this particular example, water is being driven out of a crystal in a tunnel, and they take X-ray diffraction measurements. With this tool, we can allow them to know immediately, or within minutes or hours, what the changes are in the crystal in terms of occupancy of oxygen sites and so on, that they weren't able to tell before. And then finally, in a related way, help identify things that they didn't expect during synthesis, for example. This was an example using Raman. There was a database that lists the Raman spectra of different crystals, and then our colleague synthesized vanadium sulfide, VS4, but then didn't find the same peaks. It turns out using these calculations that peak is most likely from some type of impurity, but by being able to do the calculation, sort of in reasonable amount of time to fit the experiment, as well as having reasonable structural energy, we're able to tell, not just rely on existing database and identify new phases. All right, so in conclusion, I think I'm just on time. We talked about this particular problem of trying to invert characterization data, trying to find where the atoms are given the experimental measurement. And we use atomistic modeling, both DFT and also some empirical potentials to help that process by using multi-objective genetic algorithm and computer vision. In the process, we also developed some approach to get more accurate or more efficient energy evaluations, such as force fields. So this work was funded by the Department of Energy. We are a user facility. That means that anyone who's interested in the world, who's do open science research, can apply for time. We have a small cluster, a smallish cluster now, about 3,000 cores, but we are planning on an expansion. So if anyone's interested in computer time or any of the previous computational abilities, or if anyone's doing experiments, any kind of experimental facility, we are certainly open and happy to entertain. Thank you very much for your attention, and I'd love to take any questions.
So, any questions for Maria?
Everyone wants to eat. It's very important.
Coming up to lunch.
Yes. Yeah. Yeah. Yeah, yeah. So and that is an excellent question. A lot of this has been, people have been trying to do this for a long time, such as like with bond length requirement, and they also always use a weighted approach. So you add the objective 1 plus some weight times objective 2, or if you have more. So this approach has this problem that the answer will depend on what your weight is. But the multi-objective approach is much better in the sense that there's no weight. So you explore the space. We weigh we don't weigh. We bias the search towards the lower left corner, essentially, for both objectives. But we don't just try to look for one objective. So the sampling occurs over the space, just biasing towards the lower left. And once the sampling is done, we look at the Pareto front. So all the solutions that aren't bested by another solution in both objectives. And then we look at those, and those are all the possibilities, essentially. Yeah. So it's in a one-shot approach without, considering all different weights. And in fact, people have been interested in using this now after a discussion when you have two objectives that are two different types of experiments. So people have like X-ray and neutron diffraction, and they were weighting it before, and they run into problems also. So, yeah.
All right, let's thank the speakers again.